And we're going to start with question number 5.18. This one gives us, it's telling us we have a sample of dry air. I'm going to draw a little picture here just so we know what we're dealing with. 93 liters of dry air. And it says we're going from T1, which is 144 degrees Celsius, to T2, which is negative 22 degrees Celsius. And we're at constant pressure, so P1 equals P2. Nothing changing there. And what we're supposed to find is the final volume after the temperature decrease. And in your head, you should realize that the volume is going to decrease because the temperature is decreasing. Now, our relation that we're going to use is the PV equation. PV equals nRT. Now, the trick here is to pull all the variables to one side. So PV over nRT equals 1. So this is true for all ideal gases. So if we have P1, V1, N1, and T1 equals the same thing as P2, V2 over N2, R, and T2. So we're relating the beginning variables to the ending variables after the temperature decrease. And we see here that we have R is the same on both sides. Those will cancel. The moles stay constant. No change in moles. Those can be crossed out. And the pressure is constant. That's given in the question. So now we have a relation between V1 over T1, which is equal to V2 over T2. So since this is what we're trying to look for, we're going to pull this out to the right side, to the left side, which is V2 equals V1 over T1 times T2. And one thing to be careful of is having your temperature in Kelvin. You almost always want to convert your temperature to Kelvin. When in doubt, convert it, because this is your absolute temperature. You can't go wrong with Kelvin. So the volume 1 was 93 liters, and we're multiplying that by T2, which was negative 22 plus 273. This is going to be in Kelvin now. This was our conversion to Kelvin. And put that over T1, which is 144 plus 273. This is also in Kelvin. So Kelvin's going to cancel, and we're going to be left with liters here. And your final answer is going to be 56 liters. All right, we do another relation problem. This is going to be 5.22. And for this one, we're given moles of argon, and it's in a certain size container at a certain temperature, and we want to know what the pressure is. So we have our container of argon, and moles of argon. We're going to designate moles as N. So N argon equals 1.47 times 10 to the negative 3. And then we also have temperature and the volume. Temperature is 26 degrees Celsius, and the volume is 75 milliliters. And we want to find the pressure. And this has to be in torr. Now our relation again is, for all these variables, is PV equals nRT. We're still assuming this is an ideal gas, so we can use our ideal gas equation. Now we're going to plug in moles, temperature, and volume to get pressure. We have R. R, there's two different conversions for R. There's R equals 8.314 joules per mole Kelvin. This you guys used in previous chapters. And for this chapter, you also have R equals 0.03821 liters atmospheres over Kelvin moles. Now this one has to do with energy, so we're not going to use it. We're going to use this one because it's got volume, pressure, and temperature in moles in here. So using that R, and we're trying to find pressure, so we're going to put pressure off to the side by itself. So we have N times RT over V. And plugging in our stuff, we have 1.47 times 10 to the negative 3 moles times 0.0821 liters atmospheres over mole Kelvin, and times temperature, 26 degrees Celsius, over the volume, 75 milliliters. Now, I don't know if you see the problem here, but temperature is in Celsius. We don't want Celsius because our R is in Kelvin, so we'll fix this by adding 273 to get kelvins. And then we also have milliliters on the bottom, but our R has liters, so we need to make a conversion from milliliters to liters. So we have 1 liter is equal to 1,000 milliliters. That way, milliliters cancel down here at the bottom. You're left with liters. Liters cancels here. Moles cancels with the variables in the R, and then atmospheres, whoops, atmosphere stays. We're looking for pressure. Kelvin cancels, and then we're left with atmospheres, and this ends up being 365.6. Oops. We also forgot one more conversion. We don't want this in atmospheres, we want this in torr. Gonna get some space over here. So to convert from atmospheres to torr, we have 760 torr per 1 atmosphere. And as a student of chemistry, this is just a good thing to know, pull off your head. So after this, atmospheres cancel in here, and you're left with torr. So after we do the math on this, it ends up being 365.6 torr, which is about half an atmosphere. Do you want more? Okay. All right, I'm gonna do one more. Nobody saw it, right?
Yeah, I hope not. Like, you popped this way.
Somebody walked in here, and I don't think you popped in front of the camera. So we're going to do one more, and this is problem 5.32. And on this one, this is going to be using a little bit more in our P-Nerd equation. It asks for the density of freon, and it gives it at 120 degrees Celsius and 1.5 atmospheres. And we are supposed to find the density. This is freon. That's kind of them to give the molecular equation. We're going to need this because we'll find molecular weight with this. So it's asking for a density of freon. And density, as you know, is mass divided by volume. And we have temperature, pressure. We know how we can relate those as PV equals and our T, we have temperature, pressure, and R. However, we don't know volume, and we don't know the moles. But we are looking for mass divided by volume, so we're going to have this in our answer. And moles, how do we convert moles to mass? We just multiply by the molecular weight, which will be grams per mole. Moles will cancel, and you'll end up with a mass. So we're going to pull these two variables on one side. We'll have P over RT equals N over volume, moles over volume. And we want mass over volume, so we're going to multiply that by the molecular weight. So we'll have moles times molecular weight, which is, you have to calculate it using this formula right here. You've got carbon, fluorine, and chlorine, 3 chlorines. Add that all together and you get 137.86 grams per mole over the volume. So, putting our variables in here, we have 1.5 atmospheres over 0.0821 liters atmospheres over K mole. This is the R. Also over 393 Kelvin. We had to convert our temperature to Kelvin again. 393 Kelvin. Don't want that in Celsius. And then all of this equals 5.86 grams per liter. Be careful with sig figs, because this could have been 5.8 if you had it at 5.8581. This is what was in my calculator, and if I was to round, it would go to 5.8. But if you use 3 sig figs, it would be 5.86. So be careful if you don't find it on a multiple choice. And that'd be it.